Hello and welcome to the second episode in the closed loop control series, proportional and feedforward. Let's get started. Velocity feedforward. With velocity control of a DC motor, a constant voltage inherently provides a steady, consistent speed response. As such, a constant voltage can be pre-calculated and added to a closed loop controller to bring it closer to the set point. This is called the feedforward and is an open loop method that improves the quality of closed loop velocity controllers. Mathematically, the simplest feedforward calculation is the maximum voltage divided by the free speed of the motor times the set point speed, and that will give you your feedforward in raw voltage. This will bring the closed loop controller closer to the set point, which is very important, as I'll demonstrate soon. So here we have a simple feedforward. At the bottom you see I have a screenshot of the actual Python code that's used to generate the control output, just for clarity. But if you need a little more context about how this simulation was created, please watch the previous episode, Chapter 1 of Closed Loop Control, where I go in a little bit more in depth into where the simulation comes from. As you can see, we still have a significant amount of steady state error after the speed curve flattens out. However, after some experimentation, you can apply a correction value to calibrate the feedforward value so that it does meet the set point very closely. In this case, I needed about 17% extra feedforward voltage in order to closely match the set point. Next, proportional control. Instead of 100% response, as in bang-bang control, which was in the last episode, proportional control applies a fraction of the response, which is proportional to the error. The ratio between the error and the proportional response is called the proportional gain, or Kp. The procedure of adjusting control gains to achieve optimal control performance is called tuning. A close starting value from which to tune your controller can be estimated by choosing a reasonable response, let's say 3 volts, for some fixed amount of error, let's say 1000 RPM. Therefore, our starting value for Kp is 0.003. This is what that gain looks like when applied without any feedforward. So we can see that we come up and we flatten out even further below the set point than the feedforward did. And on the right, you can see the voltage drops to about 5 volts during this time, even though we obviously need a lot more voltage to reach the set point. This is because as the process variable gets closer to the set point, the error drops. And as the error drops, so does the proportional response. And as you can see, the drop in the proportional response is so great that it actually cannot get up anywhere near the set point. So the way we fix this is we add the feedforward to the proportional control. The way we don't fix it is by increasing the proportional gain like crazy. This is how much I had to increase the proportional gain to get it to even reach the set point. I had to increase by a factor of about 33. And as you can see, we've basically turned into an even worse bang-bang controller. This is not desirable at all. The correct solution is to add the feedforward to the proportional controller. As you can see here, the simple feedforward still doesn't get us quite all the way to the set point. So we need to add the calibration value from earlier. And here we go. It looks very similar to the calibrated feedforward curve, but you'll notice if you compare the two side by side that they actually converge onto the set point faster with the proportional control, which adds some extra oomph to the response. Now let's compare the effect of control frequency on proportional controllers versus bang-bang. So in the center we have 50 Hertz bang-bang from last episode. On the right we have 50 Hertz proportional control with feedforward, and on the left we have 10 Hertz proportional control with feedforward. As you can see, the difference in the proportional controllers due to frequency is very minimal. Actually, the lower frequency proportional controller happens to get up to the set point faster, and that's just because of where the set point happens to be. If the set point was a little lower, it might have overshot and had to come back down on the next controller frame. But as you can see, if you remember from last episode when we compared control frequencies, the bang-bang controller is almost entirely dependent on the control frequency for the oscillation, whereas proportional controllers, they really don't care. They can operate at very low control frequencies and still produce good output. However, do keep in mind that a lower control frequency does produce more lag of a changing set point. As you can see on the left versus the right, the lower frequency controller has a harder time keeping up with the changing set point. As you can see here, with Bang Bang, you need very high frequencies to even approach the set point. However, Bang Bang does have the advantage of having less bias in the oscillation. So if we go back, the proportional controllers lag behind the set point, while the Bang Bang controllers ride on both sides of the set point. They lead the set point and they drag behind it. So there's less bias there, which can lead to slightly less error in the position if you're using this velocity controller for a position controller. We'll talk about that in the next episode. Let's explore the effect of gain on the controller. In the center, we have the arbitrarily chosen gain from before, on the left, an order of magnitude smaller, and on the right, an order of magnitude higher. You can see that the gain has a profound effect on how closely the process variable follows the set point. The case on the right is what we call optimally tuned, because the maximum error is so small that it barely makes a difference in the overall set point. If you think about it, that plus or minus 15 RPM is less than 0.5% of the total set point, which, however, you don't want to overtune your proportional controller. Overtuning is what happens when you increase your proportional gain so much that you actually start oscillating it again, because you basically turn back into a Bang Bang controller, because any little bit of error is automatically almost, complete full response. When you start to oscillate the error more and more, faster and faster, the error and lag will increase. And this is not really something you can fix with a higher proportional gain, because once you get to the optimal tuning point, you can't get any faster. You can try increasing the controller frequency, and you will approach the set point oscillation better and better, but at some point, you'll run into the hard acceleration limit that your system can provide. And you can test this by running a Bang Bang controller and just seeing if the Bang Bang controller can keep up. By definition, Bang Bang applies the maximum effort it possibly can. So if Bang Bang can't even keep up with the oscillation in your set point that you're expecting from it, then no proportional controller will be able to either. That's just a physical limitation of the system and its inability to oscillate at the frequency that you were requesting from it. So you need to change something about your requirements or your mechanical system if you're running into this kind of limit. That's all for today. Thank you for watching. Next time we'll be doing position control with a motion profiler, which will use all these building blocks of velocity control to achieve position. Thank you.